So I'm going to talk about a popular recommendation algorithm, a type of algorithms called collaborative filtering. And there's a nice empirical observation about a specific type of collaborative filtering algorithm that we'll try to explain or at least understand to extent in this talk. This is based on joint work with Kai Kressler, who's there, but I'll show you a better picture of him and Louis work. Okay. So let's just sort of quickly recap what I mean by recommendation system. If you have not seen him, that's how he looks usually. And he's Cohen and Thomas. He does like that book. And then there are a few other books he has read, by mistake sometimes. And then there are a few other books that he has read, some by mistake, some not by mistake. And I'm sure you'll be curious why I put the last one. We can ask that to him. In any case, this is what Guy has read, and this is what he has liked, and we know that. Now comes Louis. Louis is also like him, smart kid. So he's got read a few good things and not so few good things. And now based on this, I want to sort of, Louis wants to figure out what are the other books he should read. Well, looks like his and Guy's interest match pretty well on things that they've read. So maybe he can sort of take recommendation from Guy or his history and figure out what he should do. Well, it looks like from his history, he's going to dislike this and he's going to like this and so on. So what I've done here is that for Louis, I found users with similar preferences and then used them to extrapolate what Louis' preferences would be on things that he has not seen. This is what's known as most of us know, called user-user collaborative filtering. Okay. Now, myself come in, I'm here, so I haven't put any prettier picture of me. I come in and I'm, let's say I've just read one book and nothing more. What should...
Good enough. Right? That book is good enough. That's it. That's a great book you need to read. Nobody can recommend any other books.
All right. Let's get excited so I put it's all downhill. So, with that caveat, let's assume for a second that I want to read something more. What are the books I should read? Well, it looks like I like this book. And this book is like these other books. And since I like this one, maybe I will like those too. And hence maybe the recommendation should be that, hey, go read one of those two books. This is called item-item collaborative filtering. That is, I found out things that I liked, and then I found out the items that are like those liked items, and then I sort of recommended myself those things. Okay, and the purpose of the talk is to try to understand this item-item collaborative filtering. Now, of course, in practice, if you look at it, there's lots of details that sort of go beyond just this kind of simple explanations, and I'm not going to talk about that. For the purpose of this talk, I'm going to think of a generic item-style paradigm and try to see sort of what we can do with it.
I'm not confused with the distinction between item-item and user-user. What is the difference?
Thank you. Okay. So here it's me.
Yes.
I'm going to look at items that I have liked. In this case, Cover and Thomas. And I'm going to look at all the items that look like this one. These are all the books that are like this one. Well, how do I figure that out? Well, let me look at the history of this book in terms of users. Well, this book has +1 here. This also has +1 here, like this. This one also has +1 here, like this.
But this is a rigged data set. It could be that both Guy and the other gentleman that I do not know also really liked, Dilbert, right? And so
Sure.
Dilbert is not very much like Cover and Thomas. Right?
Wonderful. And in particular, it's like this along this dimension has nothing to do with these two dimensions at all. So in some sense, that's the whole point. Let's try to understand.
Okay. All right.
It's a great question, actually. I should have included that in part of the talk. Thank you. Okay, so this is what we want to sort of actually understand. When can sort of item-item collaborative filtering work and why and how well? Okay, so just to sort of, at a high level, this is a basic model. I've got some users, I've got some items, and for every user-item pair, there is a preference of user for that item. It's a +1 or -1. And it's a sparse matrix that I know, and based on this, I want to figure out for all the unknown entries, what would that be? Okay, and once I know that, I have a reasonable prediction for that, maybe I can decide which items to predict for, recommend to which users. Okay. All right, so which algorithm do you use? I'll just explain to you two sets of algorithms which are primarily the nearest neighbor based or known as collaborative filtering algorithm. The user, and item. There are many other algorithms for this problem, and here's just one broad category of algorithm, matrix completion. There's a very long list of work, as most of you might know, on this topic over the last 5 to 8 years, and some of those have include that. It's great, interesting intellectual development. There's another class of algorithms called primarily a reinforcement learning style, and here are a few references in the ones that I've not listed here. Primarily what these try to do is try to balance some form of explore and exploit just in a standard way. So you learn some things about unknown things using exploration, and then you try to exploit to get better. All right. In this talk, I'm going to focus on this class of talks, this type of algorithms. In particular, we were inspired by this nice, simple observation saying that it seems in practice, item-item collaborative filtering does work better than the user-user. And the question is that, if so, why, and can we explain in some form? Okay. So I'll try to set up a simple, meaningful model for this class, and I'll try to understand under what sense this algorithm might work well. So here's a very simple model. I'm going to assume there are n users. Okay. Each user has preference in terms of +1 or -1. I could assume that there are some number of items, let's say m, and then each item can be determined by preferences of the n users. That means that for each item, I can associate a binary string of length n. Alternatively, I could think of items as coming from a distribution on +1, -1 to power n. And presume that I can draw infinitely many items as per this distribution in IID manner. Okay. If you have finite set of items, we'll see what happens. But for the purpose of most of the talk, let me assume that I can draw it. Okay. But it's coming from a prescribed distribution. Okay. Effectively, there's no loss of generality. Any questions? Okay, so each item is determined by just this binary string.
So it's ID, each item is drawn ID from the same distribution?
From a given fixed distribution. And if I have finite, effectively I'm saying this is my population empirical distribution. All right, and here's how I will at least try to understand the performance of algorithms. So I'm going to say that my system is time clocked at each time. I'm going to choose one of the n users at random. And this random user is provided a recommendation as per some algorithm. And the question will be how well am I doing? Well, I'm going to earn a reward if the item that I recommended to this user, actually she or he likes that. I'm going to lose if the other way around. And the goal would be to effectively, for any time t, or to maximize the total amount of reward I have earned. Good questions so far? Now, this is very good, and especially if one is looking at this kind of objective, as t increases, one would like to see the you're earning reward effectively all the time, if feasible. Is another piece in any practical system that one would care about is that you get onto the system, and the first thing I want to make sure is that I learn your preferences very quickly, so that I can start giving you recommendations that's better than random. Okay. And one way to capture that is to actually try to find out that minimize the time it takes for me to give you meaningful recommendation. And meaningful recommendation would be a recommendation that's better than just giving you random items. Okay. Right, so these are the objectives. More formally, here's what we'll look at. We'll try to minimize the expected regret, defined as this. That is, implicitly I'm assuming that since I've got infinitely many items, in principle, I could, for every user, find out an item that he or she likes. Which means this is the best I could do, and then sort of I'm going to look at the difference with it. And is that sort of to normalize the random selection of the users. Okay, and the other one is the cold start. Is I want to find out the smallest time it takes after which, if a user is recommended an item, the likelihood of user liking that item is better than the random item. Alright, and I'm going to impose the following constraint, which is going to make the problem interesting. It's very meaningful for this setting, is that recommendations for users are never repeated. There are two ways to look at it. But if you have consumed a movie, it's unlikely that you would like to consume the movie immediately. Now it's debatable. Some movies you might want to consume again. If you have purchased a computer right now, you're unlikely to buy another computer immediately. On the other hand, if I'm going to recommend you a restaurant that you already like to go, there's no sort of nothing exciting about that recommendation algorithm's performance. So really, what we're going to evaluate the performance of a recommendation algorithm on things that algorithm doesn't know about users' preference on. Okay, and that's why we are imposing this. Okay. So again, we have a situation where a user is always recommended an unseen item, and now sort of given the setting, you see that, as Mahmood pointed out, unless there is some structure in terms of how users choose items or how items are liked by users, there's nothing, you can't do anything better than random. Formally, for example, if you have distribution mu, which is described by users' preferences on items, and if it's uniform, then no algorithm can do better. There's no information. Okay. So you want to impose some structure. Okay, so what structure? Well, here's just one experiment that we did. This is a popular movie lens data set, and then took the densest submatrix of that movie lens data set, and then we plotted where the color, the black and white scale is to sort of, it's quantized +1, -1, and the dark and bright color reflect the sort of the similarities. And we've sort of permuted one way or another. To sort of give you an idea, this looks like very blockish. Actually, it seemed to suggest that maybe there are a few distinct types of items that are out there. So it makes sense. Okay. A more generic way to think of this is maybe the distribution has some finite doubling dimension. Okay. And classically, one would think of doubling dimension notion in the context of metric space. You could easily sort of see a natural variation of this for distribution as follows. So let's imagine that these are all possible +1, -1 about n strings. Now let me take any ball in that space, and let me sort of increase its radius by 2, and the probability mass of this larger ball is no more than 2 to the power d times the original ball. Okay. And I want to find the smallest such d. Okay. And the smallest such d would determine the doubling dimension of mu, and will require that it is finite. Now, if you think of the uniform distribution, the uniform distribution is effectively n or n minus 1 as a dimension, so it's not finite. And of course, there you're not getting any collaborative gain effectively. The hope is that if I have smaller dimension, then maybe I can gain some more. For example, if you have few types, let's say k different types, and types are the mixture of delta distributions, then dimension it's easy to see, irrespective of gaps. It's no more than log k. All right, so this is the basic structural assumption we'll make. And now so we'll try to ask a question. How well can an item-like collaborative filtering algorithm? Any questions? Yeah.
So types, uniform distribution, and then how many types are there? There are n types, then you have log n. What do you mean by type in this case?
Good. So let's...
Not in the information series?
No.
Okay.
No. So, yeah. So it has nothing to do with information theory.
Maybe write on the whiteboard what this mu is. Mu is the distribution on the, what is n? N is the number of users or number of items? I got confused already at this point.
Yes. I think that's right. Okay, so I've got n users. And for purpose, let's think of items. There's an infinite pool of items from which I can pull. And each time I pull an item, I'm pulling an item from a distribution mu. And mu is over -1, +1 to power n. So for example, I pull an item from here. Let's say item comes, and let's suppose for a second n equals to 3. An item comes out to be a string like this, -1, +1, -1, +1. This is one item. What this would mean is that user 1 likes it, user 2 dislikes it, and user 3 likes it.
So your original question was to understand the differences between item collaboration versus user-user collaboration, right?
That's correct, but for the time being, I'm just going to try to understand how well item-item collaboration.
Yeah, because your model seems to be asymmetrical, right? Because you're putting you could easily put a distribution
on
row on users.
Yes. So this sounds asymmetric right now because I made this infinite. Let's say for a second, make it finite. Let's think simply in terms of finite types, where a type is, one way to think of a type in a very sort of simplistic form is, well, each item is coming from a mixture distribution of k different mixtures, and each mixture is the delta distribution, a delta distribution on one of the binary strings. Okay. So in that case, if I have k types on item space, it will lead to naturally no more than 2 to the power k types on user space. So there is a nice sort of symmetry between these two problems. And the reason I'm looking at this variation or this asymmetry, because I fundamentally want to analyze the item-item version.
I don't understand, because let's look at a matrix, right? You can think of you're finding a way to generate this matrix.
That's correct.
Right, but here you are assuming some correlation, because mu is not ID across users.
That's correct.
But across items is independently drawn from the same distribution.
That is correct.
So there's an asymmetry in terms of generating this matrix.
Yes, so you could imagine, so if you start sort of thinking of that way, it will look asymmetric, but if you think about, let's suppose I've got a population of items. There's no distribution yet. So I've got m items. Now I'm going to look at histogram of the distribution that these items would induce on -1, 1 to power n. Since for the purpose of the recommendation algorithm, how do I label the items does not matter. Effectively, it looks like as if sort of if I started generating matrix by picking columns, it would look like as if sort of I'm choosing okay, up to errors items uniformly at random. Not items at random as per given distribution. Okay, so all right, so this is the setting, and now I want to understand sort of how well I'm almost done, right?
You have 5. Devavrat, could you run the same argument on the users? The users, you don't have to label them either.
That's correct. So you can run the same argument on users, and that will lead to user collaboration, and it would have worse performance than what I'm going to show you here. And I think we spent last year going through that. And that's why there was this tiny reference that I put down for the data set. I will talk offline.
Okay.
Let me sort of get to the punchline in 3 minutes. Okay, so here's what I'm going to analyze. Is per user average regret, defined as this. I'm going to assume that when a random user looks at a random item, the likelihood of their liking is new. So this is like saying that sort of if I recommended a random user a random item, this is how well I'll do. Now, definitely I want my algorithm to do better than this. And so if I start looking at my regret over time, what's going to happen is that maybe initially I have no idea. I have no information about users. So maybe I will do terribly. And effectively, I'll do as well as random recommendations. But maybe after a while that I will learn something about the system, this is cold start, learn up something about the system, maybe I will actually do well and I will actually have my regret growing sublinearly, which is pretty good. It's effectively saying that I'm recommending good items with pretty high probability. And then after some time, because I've got limited users and I'm sort of thinking of item pool infinite, maybe I won't get any more collaborative gain between users. And after that, my regret will be linear, but just scaling at much smaller rate. And this is effectively user limited region. Now, if I did not have infinite items, if I have finite items, maybe I'll have to stop somewhere here in the middle. Right. So this is the style of result one would expect. And first question is that how well a cold start will do under these assumptions. So I'll effectively tell you the cold start scales as this, where this is the constant that's coming from the random fraction of items that are liked, and depends only on dimension and nothing else. So it's a good news because it doesn't depend on, for example, number of users. Is this the best one can hope for? But ideally, one would hope that if I'm a user, think of sort of the first slide example that I showed you. I'm a user. How long does it take me to get a first good recommendation? Well, if nu is a fraction, then it takes 1 over nu fraction to sort of get a first good recommendation. Maybe after that, the best algorithm should actually start giving me good recommendations after that. And we believe that that should be true, but we don't have a proof yet.
What's D?
D is the dimension of the distribution.
What is theta?
Theta, I mean the order theta. And the condition of it. I should use the big theta or the small theta.
I thought some function.
I meant this theta. Sublinear regret would scale effectively like this. So as the dimension comes into play, if smaller it's better, if larger it gets worse, as you would expect. And finally, the time till which you can get nice sublinear regret depends on the number of users. And after that, your slope is scaling down like this. So more number of users you have, better you will do. I think I should stop here. I had an algorithm at a high level. It will look something like this. Let me sort of put the summary slide here and stop. Thank you. Yeah.
The block of the regret, is it for this algorithm or it's
No. So that is for primarily item like so it's not clear if this is the best.
You raised expectations about telling us why the two sides of looking at it are different. Can you, maybe with the graph or something, now say why one of them has intuitively better performance?
Yeah, good. Actually, what is the intuition wise of user might not do well? Okay. The reason is the following. Here, what I'm doing is that so I'm a user, and so I've got an item space, and I've got to figure out sort of what are items similar to each other. But if I sort of look at just sufficient items, then what I can do is that the cost of exploration I can sort of spread over users. So every user, while he or she is coming in the system, it's a very small amount of time per user that they will spend to actually explore collectively, and after that they will get benefit. On the other hand, if in the user case, what you would do is that you will have to explore all users. And when you explore all users, each user has to pay cost of their own exploration. So that means that it will take longer for them to start getting good recommendations. So there is a fundamental asymmetry in the problem itself, and that's why item might be better. Yeah.
So is there any reason why you see the exponent d plus 1 over d plus 2?
There's no fundamental reason I can tell you top of my head, at least the way it looks like the way sort of one would imagine going with this type of approach. I don't have any fundamental lower bound, but I would believe that at least the way we have looked at the problem, we wouldn't be able to improve it. Like you see similar exponents showing up in other bandit-like settings as well.